Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the concept of light refraction, where we will cover what is light refraction, what causes light refraction, and calculating refractive index. This video is designed for those who are taking IGCSE Physics. So, if you are taking SPM Physics, please watch my video on light refraction designed for SPM students. Because if you're taking SPM, you will be learning a little bit more than those who are taking IGCSE. So, let's not miss out on some of those important concepts as well. This video is designed more of an introduction to light refraction and also can be used as a revision piece, an overview of this particular concept. We will not be going through any worked examples or calculations in this video. Those will be covered in another video. So first things first, what is light refraction? By now, you should know what light refraction is, or at least how it appears in real life. For example, if you place a pencil in a cup of water, you will find that the pencil appears to be bent. And of course, by now you should know, oh, that's because of light refraction. But how do we learn this in theory? So normally, when we want to study light refraction, we will use the example of a glass block placed in air, and we will observe how the light ray travels between air and glass. So let's say we shine a single ray of light from air into the glass. So this yellow arrow here represents that single ray of light. And the arrow, of course, indicates its direction. Now, when the light travels from air into the glass block, we'll find that the light ray changes direction. And then when it travels from glass back out into air, it changes direction once again. So light refraction is the phenomenon where the light ray changes direction as it travels through different mediums due to its change in speed. You must, of course, also be aware of what causes the change in speed of light within these different mediums. And that's because of the different optical densities of the different mediums. Now, some of you may have learned that its density. What is its optical density? Some of you may never have heard of it before. So let's take a pause first. My question to you is, how does density affect light? So see, density is a calculated value where we take the value of the mass divided by volume. So density is the mass per unit volume. One of the first learned and understood density is by comparing density of materials against water. So you place a different objects in water and see whether it floats or it sinks. And if it's lower density, it floats. And if it's higher density, it sinks. So think about all that floating and how heavy it is in water and all that. And think about how that affects the speed of light. The answer, it doesn't. You see, density is more of a comparison of how much mass, how much matter there is in every unit of that volume. But when we talk about speed of light, it's about how fast that light ray can travel through that particular medium. And of course, light can only travel through transparent or translucent mediums. If the object, if the material is opaque, then light cannot travel. So not all objects allow light to travel through it. So all objects have density, but not all objects have optical densities. So that's an important thing to consider. Therefore, density has no effect on the speed of light. So what affects the speed of light is actually something called optical density, which is the measure of how much light has been reduced in that medium. You can think of it as, because density is like how much material there is within that small volume of an object. So optical density could then refer to the amount of the atoms or the particles in that transparent or translucent medium within that small area. So of course, the more particles there are, then the higher the optical density. And then you think, oh, if there's more material packed in that small area, would it be easier or harder for the light to travel through? Well, obviously, if there's more material, it's harder for light to travel through, right? So that slows the light down. That's why the greater the optical density, the slower the speed of light. So more correct way from this point forth to understand how the speed of light in a medium is affected is that it's not affected by density, but by the medium's optical density. Next, let's look at the calculation of the refractive index of the medium. Now, before we get into that, just to point out to you very quickly, because air has a lower optical density, light will travel faster, whereas glass has a higher optical density, so light will travel slower in glass. So when light travels from air to glass, you can see how the light ray appears to refract towards the normal. So the normal line is a line that is perpendicular to the boundary. And then when light travels from glass into air, because it's moving from slower to faster, it now refracts away from normal. So again, when light travels a from faster to slower, that means from a lower to high optical density, it refracts towards normal. Whereas when light travels from slower to faster, that means from a higher optical density to low optical density, it refracts away from normal. So that's also an important uh, terminology that you need to learn to use. You need to know how to describe that kind of refraction. So let's learn to calculate the refractive index. So refractive index is something like optical density, but they're not exactly the same. They are related, but refractive index is more of a physics way of calculating how much light has refracted, if you will. So if you remember that in physics, we like to measure everything, right? So it's not enough that we know, oh, light refracts, when traveling through different mediums. Not enough for us to know that, oh, refracts towards and away from normal. We also need to know by how much. So by knowing the exact value, this enables us to predict more accurately how light would refract in different mediums at different angles. So refractive index is actually the ratio of the behavior of light in air and the different medium in terms of refraction. There are a few formula that we can use to calculate refractive index. So the first one obviously relates the speed, because we know that light travels at different speeds in the different mediums. So when we calculate the refractive index, it's always a refractive index of the medium. That means if we have a glass block, we're calculating the refractive index of glass. If we want to observe how the light bends in water and we want to calculate the refractive index, it's the refractive index of water. At this stage, you will not be counting refractive index of air, because the refractive index actually is a comparison of the refracted light ray in that medium against the refracted light ray of the light in the medium against how it travels in air. So the refractive index is comparing the medium against air. So that's why we're not calculating the refractive index of air at this point. If you are wondering, can we compare the refractive index of one medium to another, like from glass to water, or comparing, water to oil, for example? It is possible, but that's not something we learn at IGCSE level. That's something you will learn at higher levels. So for now, at IGCSE level, we just focus on comparing the medium against air. So that's why the formula here, as you can see, is the speed of light in vacuum or air divided by the speed of light in medium. Now, why is it vacuum or air? Because at this stage, we take the value of the speed of light in vacuum and air to be the same. Are they different? Actually, yes. But for now, we assume that difference to be negligible. So at IGCSE level, we take the speed of light in vacuum and air to be the same, which is 3 times 10 power of 8 meters per second. Another way to calculate it is by comparing the angles. But first of all, we need to know a bit more about the terminology used. So again, let's look at the names of the rays. So the light ray that's traveling from the source is known as the incident ray. When the light ray refracts in a medium, that ray is known as the refracted ray. And the light ray that comes out of the glass is known as the emergent ray. When we want to measure the angles, it is always measured from the normal line. The normal line is a line that is perpendicular to the boundary. So as you can see, I've got the gray colored lines here that are dotted, and these gray dotted lines are perpendicular to the boundaries at the point where the light is changing the mediums. So for example, on the top here, when the light is traveling from air to glass, okay, we've got the normal line there. The angles are measured from the light ray to the normal line. So it's always measured between the light rays and the normal line. So on the top here, you can see I've labeled the angle as I in air, and I've labeled the angle in glass as R. So that's how we measure the angles. Now, because in air, that ray is the incident ray because it's coming from the source, that angle is known as the angle of incidence, or also known as the incident angle. The light ray that is traveling in the glass block is known as the refracted ray. So the angle between the refracted ray and the normal line, which I've labeled here as R, is known as the angle of refraction or refracted angle. So that means that you can call the angle either way. Angle of incidence and incident angle, same thing. Angle of refraction or refracted angle, same thing. So not only is the ratio of the speed of light equal, we'll find that the angles also have a ratio, but the angle is not just I against R. So the people, the researchers, the physicists who have done all their research on light, refraction, and all that have found that the ratio is actually based on the values of the sine of the angle. So another way to calculate the refractive index is to take sine I divided by sine R. By the way, the name of the person who came out with this refractive index, his name is Snell. We'll come to that at the end of this video. A little bit about sine I and sine R formula first before we move on. So this is of course comparing the angles when light is traveling from air to glass. But what if we were given angles in the situation where light is traveling from glass to air? Now, based on the name, I know I've written here incident ray, refracted ray, and emergent ray. But let's say if we focus only at the bottom part where the light is traveling from glass into air, if you just focus on that section, that light ray moving from glass to air, it becomes the incident ray, and the one moving out into air is known as the refracted ray. So hence, the angles are I and R respectively as well, where I is in the glass block and R is in the air. But the problem is if you take sine I over sine R based on this, it will not be the same as the one on top, right? Because you can see that overall, the angle of air should always be bigger than the angle in glass. So then it's like, okay, how do we apply this then? If you're wondering, because at the bottom here, at the bottom part where light is traveling from glass to air, the value of I and R are opposite to the values of I and R, which is on the top. Okay, if you don't know what I'm talking about, it's like basically you can't just take sine I over sine R blindly because you've got a whole bunch of different possibilities of I and R in this case. Now, the calculation of refractive index is always based against the comparison of the light traveling in air. So we always take it as light traveling from air into the glass. So even if it was flipped, where light travels from glass to air, although in terms of the names, it's still I in glass and R in air, but when you apply the values in the calculation, I should be the angle in air while R is the angle in the medium. Because you must remember that the comparison of the angles here, the refractive index calculations here, are always based against how light travels in air. So we take I, no matter whether it's I in, in this case it's in the glass or something, doesn't matter. Okay, that's the name. But when you do the calculation, however it goes, I must be the angle in air and R must be the angle in medium, even if light was traveling from glass into air. A little bit about Snell's law. if you'd like to know more about Snell's law, if you were to Google it, this is the formula you would get, where you'd get n1 sine theta 1 equals n2 sine theta 2. So n1 is the incident index, which means n1 is it's the refractive index of the light ray. That's the incident ray. That means in air. And n2 is the refracted index, where n2 is the refractive index of the medium where the light has refracted in, which in this case is the glass block. Theta 1 is the incident angle, theta 2 is the refracted angle. So this is actually Snell's law. So Snell was the one who discovered that, oh, the angles where the light is traveling, between the different mediums, the two angles, there's actually a fixed ratio, and it's based on the comparisons of the values of sine. Now, this is a little bit complicated. This is more of an A levels kind of calculation. So for IGCSE, do you need to use this? Good news. No, you do not. So I'm just showing this to you in case you're wondering, how come this showed up, when I Google Snell's law? Yes, this is the actual Snell's law formula, but you don't need to use it. So we're using the simplified version, which is n equals sine I over sine R. Yay, good news for you. And there's one more formula, which is n equals 1 over sine C, where C is the critical angle. However, I'm not going to go through the critical angle in this video, because this is actually under the subtopic of total internal reflection, and that is a whole other concept which will take another maybe 20 minutes to explain. So instead of overloading you, sorry, let me say that again. Instead of overloading you with too much information right now, let's take that into another video where you can find out more about total internal reflection in all its glory. So this is just an overview. Here are the three formula that you need to know in terms of how to calculate refractive index. And yes, no matter what formula you use, you will get the same value for the refractive index of that particular medium. So for example, the glass block that's normally used in the school lab has a value of 1.5. So whichever formula you use, the refractive index of that glass block will always be 1.5. So I'll go through the worked examples and how to use this formula and how to answer questions in another video. For now, this is the end of this overview. Oh, and one more thing. Yes, if you're doing calculations, no matter what, because we're counting the refractive index of the medium compared to air, the value of n will always be more than 1. If it's equal to 1, it means that the speed of light in that medium is equal to the speed of light in air. That means the refractive index of that medium is equal to the refractive index of the air. So that's what it means when you get the value of n as 1. So n must be more than 1, because that indicates that the optical density or refractive index of that particular material is greater than the optical density or the refractive index of air. All right, so that's it for now. So if you enjoyed this video, if you found this educational and helpful, please don't forget to click like and subscribe for more physics lesson from your physics teacher, Miss Ho. Happy studying!